Hi guys, in this video we are going to be looking at some electromagnetism tutorial questions. Let me just give you guys where these questions are from. Now, students in the Faculty of Engineering and Technology in Boya, in the Department of Civil Engineering, they have an exam on Saturday and it's going to be on their course electromagnetism. So the professor gave them some tutorials. There are 15 exercises in the tutorial PDF in total. So I'm going to solve the ones that I can solve within this time interval, and then the remaining ones we can solve them later. But the ones I'm going to solve, then you guys are just going to follow up. So in this video specifically, we are going to be doing just one exercise. So we are going to be solving one exercise at a time. So in this video, we are going to be looking at exercise 10 of the tutorial PDF that was sent by the professor. So exercise reads: a conductor suspended by two flexible wires as shown in the figure has a mass per unit length of 0.04 kilogram per meter. There is a figure. A. What current must exist in the conductor for the tension in the supporting wires to be zero when the magnetic field is 3.60 Tesla into the pitch? And B. What is the required direction for the current? Alright, so let's begin with the A question, which is asking us to find the currents that must exist in the conductor for the tension in the supporting wires. Here are the supporting wires. Here is the conductor for that tension to be zero when the magnetic field, that is B, is pointing into the pitch. So here is B in. So firstly, we are going to draw our free body diagram. So if I take my conductor, he has a mass, therefore the weight is going to be acting downward. The mass, I suppose the mass to be m, so the weight is mass times acceleration due to gravity. Now since the magnetic field is pointing into the pitch, then I'm going to have a resistive magnetic force that is opposing the weight. I call it FB. Now from here we can consider that the system is in equilibrium. If the system is in equilibrium, it means that the sum of forces in the y direction, because here we are dealing just with vertical forces, so the sum of forces in the y direction is equal to 0. So first we choose our reference frame for the force. So we suppose that all forces pointing in the upward direction are positive and all forces pointing in the downward direction are negative. So from there we get the force pointing in the upward direction, FB, positive, plus because you are taking the sum of forces, and remember it is the algebraic sum of forces, so FB is positive because it is pointing in the upward direction, plus negative mg is pointing in the downward direction, is equal to 0. So with that we have FB is equal to mg. Now the magnetic force is given by this formula: FB is equal to BIL sine theta. Now let's define what these constants are. Theta is the angle between the current and the magnetic field. I is the current and L is the length of the conductor. Now we are left to find theta. Now what is theta? So according to the question, we're being told that the magnetic field is pointing into the pitch. So it is pointing, let's say, into the screen, for example, since you're looking at it like this. So it is pointing into the screen. So with that said, the current is either going to be pointing to the left or to the right. So with that, we have our theta to be equal to 90 degrees, because it is the angle between the current and the magnetic field. So theta being equal to 90 degrees, it means that the sine of theta will be equal to 1. So my magnetic force will simply be equal to BIL, where B is the magnetic field strength there, So sorry, I never indicated here, but B is a magnetic field strength. We have said I is a current and L is the length of the conductor. So from there we have BIL is equal to mg. Now since we are looking for the current, we can divide both sides of the equation by dl, and we get the mass divided by the length times g divided by b. Now I separated this because the value was given already. The mass per unit length was 0.04 kilograms per meter. Now our g is the acceleration due to gravity, which is 9.8, and our b is the magnetic field strength, which is 3.60 Tesla. So with that we get our current to be approximately 0.1089 amperes. Now the b part of the equation, we are being asked to give the required direction for the current. So I'm going to use two different methods to find it. The first, we are going to use this is a battery. Current moves from the positive to the negative. So from the positive terminal to the negative terminal, or from the long terminal to the short terminal. So from there we are going to see that current is going to move to the right. So current moves to the right. So we can also use the right hand grip rule. In this case, we have our magnetic field, which is this, pointing into the page. Since the magnetic field is pointing into the page, then the current is going to be pointing to the right, actually.